In this demo, we'll see how you can use modified z-scores for anomaly detection. The modified z-score technique is a more robust version of the traditional standard z-score. This technique makes use of the median and the median absolute deviation to compute deviation in the data, making it less sensitive to extreme outliers that might skew the computation of mean and standard deviation. The computation of the modified z-score is very similar to the computation of the z-score, except that you replace the mean and standard deviation in the traditional z-score with the median and the median absolute deviation, MAD, making it a more robust measure of how far a data point lies from the central trend in the presence of outliers. The modified z-score is a robust alternative to the z-score, and they are less outlier sensitive to the traditional z-score techniques for identifying anomalies in univariate data. The z-score technique has a major weakness in that extreme outliers can significantly inflate the mean and standard deviation and thereby mask other true anomalies or cause normal points to appear anomalous. Instead of using the mean and standard deviation, I-scores are calculated using the median and the median absolute deviation of the data. The median is the central value of an ordered data set. So you sort your data in ascending order and find the middle value and is much less affected by extreme values than the mean. The MAD is the median of the absolute deviations from the data's median. In other words, you find the median value, calculate how far each data point is from that median, and take the absolute values of those distances, and then find the median of those distances. The traditional z-score technique assumes approximate normal distributions and clean data. Modified z-scores, on the other hand, are designed for scenarios where the dataset may be contaminated by outliers or have asymmetric distributions. Because the median and the MAD are not really affected by extreme values, the I-score method gives you a more reliable distance from central tendency in these challenging cases. Despite the fact that modified z-scores are robust, they are not a cure-all. They still operate on a single feature at a time. They are a univariate technique and cannot detect anomalies that arise only through combinations of features. The combination of using the median and the MAD for modified z-score computation is typically robust, but it won't work well if the data distribution is very skewed or has multiple distinct normal modes. The median in that case may not fully represent the typical behavior segments, and the I-score thresholds may need some adjustment and tuning. Let's quickly summarize the pros and cons of anomaly detection using modified z-scores. These work without assuming any particular probability distribution for your data. So this avoids the fundamental limitation of z-score and statistical methods that require normality or other distributional assumptions. Modified z-scores are thus applicable to real-world data that may be skewed, have multiple modes, heavy tails, or any other distribution shape. Standard z-scores rely on the mean and standard deviation, which are easily distorted by extreme values, and they end up effectively masking the outliers that we are trying to find. The modified z-score uses the median and the median absolute deviation, which are highly resistant to these extreme deviations. This ensures that a few large anomalies do not inflate your baseline and allow other outliers to slip through undetected. When working with small datasets, a single outlier can drastically shift the mean and standard deviation, rendering the standard z-score practically useless. The modified z-score remains stable even with limited data points because the median is not pulled by a single extreme value like the mean is. This allows you to effectively detect anomalies in early stage pilot data or rare event scenarios where large historical datasets are unavailable. On the other hand, a critical limitation of this technique is when the median absolute deviation is equal to 0. Because the modified z-score formula requires dividing by the MAD, this scenario results in a division by 0 error that renders the calculation undefined. This makes the method unsuitable for sparse datasets or systems with frequent repeated measurements unless you implement specific logical workarounds. Although more robust than standard z-scores, the modified z-score still implicitly assumes that your normal data is distributed symmetrically around the median. If your data set is naturally heavily skewed, such as valid web latency data that has a long tail of very high values, the method effectively treats the long tail as outliers rather than normal behavior. This means you may need to transform skewed data, maybe using the log scale, before you can rely on the scores to be accurate. It turns out that the modified z-score has lower efficiency on clean data. If your data actually is perfectly normal and free of errors, using the median and MAD is statistically less efficient than using the mean and standard deviation. In this technique, you're ignoring the specific magnitude of the values in favor of their rank. That's what median does. You end up discarding some useful information contained in the dataset. This means that for perfectly clean Gaussian data, the modified z-score may be slightly less precise in defining the boundaries of a normality than the standard z-score.